Let's talk about energy and simple harmonic motion. That's section 14.4 of the book. And uh, we've already seen some of these basic concepts. So, for example, when we take a ball and we toss it up in the air, as its height increases, its gravitational potential energy increases and it slows down. So, its kinetic energy decreases. And then as it falls back down, its gravitational potential energy is decreasing and its kinetic energy is increasing. The same thing happens in simple harmonic motion, except that that oscillation back and forth between gravitational potential energy and kinetic energy, or elastic potential energy, if it's the case of a spring motion, and kinetic energy, just continues. So we have this cycling back and forth of the energy of the system between potential energy and kinetic energy. And that's illustrated on this slide here for a spring. And here we've got a spring on a frictionless table and everything is just moving back and forth horizontally. And when the spring is stretched out to its maximum extent, there's a lot of elastic potential energy. When you let it go, it speeds up. It reaches its maximum speed, as we've already seen, at the equilibrium position. And at the equilibrium position, there's no stretching. And remember that for a spring, the elastic potential energy is 1/2 kx squared. Remember, k is a spring constant, and x is the amount of the displacement. Sorry, for some reason I started writing that in the middle of the page instead of on the left-hand side of the page, from the equilibrium position. And so when the spring is going back and forth, as shown in the slide here, when it's at the equilibrium position, the elastic potential energy is 0. So all of the energy of the system must be in kinetic energy, and therefore that is when the speed is at its maximum value. Then since it's moving, then it's going to compress the spring, and that gradually slows the object down, so the potential energy, the kinetic energy decreases, and the potential energy increases. And so on the right-hand side of the slide here, you see a energy diagram where the horizontal line, E equals K plus U, shows the total energy of the system is constant. That line is the sum of the blue curve and the green curve. The blue curve being the potential energy, which is biggest at the extremes of the motion, and the kinetic energy is the green curve, which is biggest at the center point and goes to 0 at the extremes of the motion. And so this next slide just sort of walks you through those things. And here again, you see the potential energy for mass on a spring is given by 1/2 kx squared. Of course, kinetic energy is 1/2 mv squared, and the total energy for example, an oscillating mass on a spring is K plus USP is just going to be 1/2 mv squared plus 1/2 kx squared, and that energy is constant. That's the total energy. It's conserved unless there's some work that's done on it by some force from outside the system. So that could be friction, for example, acting to change the total energy of the system. You would get a similar thing for the other type that we've been talking about is a pendulum. And in a pendulum, the potential energy is gravitational potential energy. As the object swings up, it's higher, so it's got more gravitational potential energy, and it stops momentarily there. So if you imagine if you're on a swing, your velocity goes from positive to negative, so it goes through 0 at that point. You're moving the fastest at the bottom, where your potential energy is 0, your kinetic energy is maximum. So both of those things work the same way. It's just an interplay, an exchange back and forth between potential energy and kinetic energy. Now for the spring example, which we're looking at here, at the maximum displacement, we have V equals 0 and X equals A, the amplitude by definition. That's just the definition of the amplitude, is what's your displacement at your maximum displacement. And so that says that the energy in this particular case is 1 half times m times 0 squared plus 1 half k times a squared, which is just 1 half k a squared. So the total energy of the system can be expressed in terms of the amplitude, 1 half ka squared. Similarly, at the equilibrium position, x, the displacement, is 0 by definition, and v is the maximum velocity, v max. And remember that v max for a spring, we had, actually it's generally true, it's not just for spring, v max is uh, curly omega times a, which is the same as 2 pi f times a. So that's Vmax. We can relate it also to the amplitude. And so the energy at the equilibrium position is 1 half m Vmax squared plus 1 half k times 0 squared. So that's just 0. And if I replace the Vmax with this 2 pi Fa, I get 1 half m times 2 pi Fa squared for the total energy. Well, they're both true. The total energy isn't changing as this thing is oscillating. It is only the exchange of energy between potential energy and kinetic energy that's happening, but the total energy is constant. So both of these expressions for total energy are true, okay? And so if they're both true, then they're equal to each other. So that tells me that 1 half Ka squared must equal 1 half m times 2 pi Fa squared. My halves cancel and my a squareds cancel, and that gives me K equals m times 2 pi f squared, and I can then rearrange that to solve for f. I take the square root of both sides, and I get f equals, let's see, I'm going to have a square root of k over m and a 1 over 2 pi. So by looking at conservation of energy and evaluating the total energy both at the maximum displacement and at the equilibrium position and equating those two, I'm able to get an expression for, and that's what's shown here on this slide, I'm able to get an expression for the frequency of a spring in terms of the spring constant and the mass on the spring. And remember that T is 1 over F, so if we take 1 over that, we get 2 pi times the square root of m over k. So these are handy expressions to have when we're going through playing around with problems with oscillating springs, for example. So let's take a look at an example problem then. You've got an example that you can work through here in the notes. The tactics box, always follow these tactics boxes when you are solving these problems. Go step by step by step in solving these things. And then we've got these equation for the frequency for mass on a spring. So let's do our own example problem here. You can look at the one that the book is provided. Let's do our own example. So as it's stated here, in this example, a 5 kilogram mass is suspended from a spring. So first thing we do is draw it. So let me draw a spring with some mass, m, hanging from it. Then this is like the ceiling up here at the top, okay? And there's the spring hanging. and it's got a weight that has stretched the spring some, but if we're now just leave it hanging there, that is the equilibrium position of the spring. Oh my gosh, this thing. Oh, you don't see it, but I see it. Drives me nuts. Things popping up on my iPad. So this is the equilibrium position here in blue for this spring. Then it says that if we stretch the spring by an additional 10 centimeters, that takes a force of 20 newtons to do that. So let's now draw the spring stretched by 10 centimeters. And that took a force acting down on it of 20 newtons. And then let it go, as they say in the song. And the question is, how long before the mass returns to its starting point 10 centimeters below its equilibrium position? That is the time that we call the period of the oscillation. In other words, it's going to go up above the equilibrium position and then all the way back down to this starting point here. That's one complete cycle. And the question is, what is the period of the oscillation? Okay, so we want to know, what is T? Well, we just saw from our analysis of the energy of a simple harmonic oscillator for a spring in particular that we have a handy equation for the period of an oscillating spring, which is 2 pi times the square root of m over k. And we are told in this case that m is 5 kilograms. What is K then? We need to know K in order to get the period. Well, for that, we need to remember that the relationship between the spring constant and a force is F equals Kx. The force required to extend a spring by a certain amount is given by F equals Kx. This is in chapter 8, which we skipped, but I introduced it earlier. I can't remember whether I introduced it in chapter 10 or earlier in chapter 14, but this is called Hooke's law. But this relates the spring constant K to the force required to stretch a spring by X. The restoring force on the spring is minus Kx. That's the force that the spring is exerting on the mass to pull it back up. So you may have seen the same equation with a minus sign, but the spring constant is always a positive number. And so in this case, we know that a force of 20 newtons was used to stretch the spring by 10 centimeters, which is 0.1 meters. So that gives me K is 20 over 20 newtons over 0.1 meters, which is 200 newtons per meter. So there's our spring constant in SI units. We have our mass is 5 kilograms in SI units. So then we can just put our values in a calculator. T equals 2 pi times the square root of 5 over 200. And let's see what that works out to be. It's 1 second. Okay.